next topic of our kinetics has this interest concentration and chemical rate. We realize that most chemical reactions are indeed reversible. If I think about the collision theory, initially at time 0, I only have reactants involved. There is no product yet made. So only the collisions that are occurring are from reactants. But as time goes by and products are being made, they can indeed collide with one another. And if the orientation in space and with enough kinetic energy, they can break bonds and form new bonds going back to the original reactants. When we say that reactions are reversible, we're simply reminding ourselves that if A plus B collides to make AB compounds can collide with one another and break those bonds. At time 0, the initial concentrations, we only have reactants going on. There are no products yet. And so the earlier the reaction rate is measured, the more dependent those rates are on the initial amounts of reactants. If I let too much time go by, I start to interfere with the rate of the reaction by actually measuring a reverse process. So we call this the initial rate method. This method, called initial rate method, measures the concentrations at time 0 of the reactants as soon as they're mixed. If we know the concentrations of the initial amount of reactants and measure them several times at varied concentrations, we start to get insight with how the concentration is affecting the rate. So this method, called reaction rate method, initial rate method, measures the concentration several different times. So we run probably 2, 3, sometimes 4 different experiments by varying the initial concentrations of reactants. And we start to generate data tables. If I start with 0.1 molar of a reactant, how fast does it go? If I double the concentration, what have I done to the reaction rate? Those initial concentrations of the reactants then get varied, and we start to generate a data table that measures concentration versus reaction rate. So literally our labs have it with a stopwatch. You pour the 2 solutions together, click the stopwatch. How long does it take to see evidence of the product? You'll run the trial again, varying the concentrations, and hit the stopwatch again. By varying the concentrations and running the reaction several times, we start to generate data. But it's very important that we measure at time 0 so that we eliminate the reverse reaction effect. When we start determining rate laws, remember the last page we wrote rate expressions. This is very different. Rate laws show how the rate depends on the concentrations of the reactants. It does not, I'll repeat, it does not have anything to do with the stoichiometry. The rate expression, that's what we just practiced in the previous lesson. That uses the stoichiometry where we use those fractions. Rate laws do not depend upon stoichiometry. They have to be determined via experiment. They have to be based on initial concentrations and reaction speed or kinetics. So the only way to determine a rate law is not from the balanced equation, but from experimental data. If this reaction, and again we wrote that up above if it looks familiar, dinitrogen pentoxide decomposed into 4 molecules of NO2 and 1 molecule of O2. If the reverse reaction does not play a role, notice it's only a forward arrow. You can find the rate will only depend upon the concentration of the reactants. So we write what's called a rate law. The rate is equal to K, which will be the rate law constant, times the concentration of N2O5, notice that's the reactant, raised to some power we do not know. I'll just make up a letter called n. It is not squared. It has nothing to do with the coefficient. It has to be experimentally determined, and I'll explain how. This is called a rate law. Rate is equal to K, a constant, times the concentration of our reactant raised to some power n. The K is a rate law constant. It depends on temperature and the solvent used. And n is called the order of the reactant. It's usually a positive integer. And for the scope of this class, we'll talk about first order and second order. I might comment on a zero order. I have seen them up here in the AP exam, but they're rare. So typically, we're going to look at first order and second order reactions in terms of homework and testing. Rate is equal to K, that's a rate constant, times the concentration of our reactant, N2O5. We do not consider the product in an initial rate method. There is no product at time zero. And N represents an integer called a rate law order. The order with respect, the concentration affects the rate. Let's look at that a little further. This is from the PowerPoint slide. I didn't have it written in the note pack, so it was a visual I needed to pull up, so thanks for your patience. What we have is generating two lists, and these could be lists right into your calculator. In list 1, we have time. As time goes by, we're measuring the disappearance of the reactant. At time 0, it's 1 molar. 200 seconds go by, it's down to 0.88. 400 seconds go by, we're down to 0.78, and so forth. If we graph this data, it looks like this kind of slope. And again, we could do this on our calculator list and generate a graph, and at this point, we'll just take a look at one that's been generated. I want to find two convenient points to find how varying the concentration affects the overall rate. The first one I noticed is an intersection here at about 0.8, time is 400. Cut that concentration in half to 0.4, and again, at about 0.4, I'm down about here. I have a time of 1600 seconds. So cutting the concentration in half affected the rate from 4 to 16. This information is what's being used then to generate the next question from our notepad page. So when I find a rate, molarity per second, let's suppose at this instant in time, 0.8 per second, time interval that went by is 400 seconds, we can come up with a rate. We did the same at a different concentration. We set an average rate as time goes by, would set up molarity per second for the rate at 0.4 molar. We solved for 0.4 molar and 0.8 molar instantaneous rates. We solved for the tangent of the line, molarity per second. How did changing the concentration affect the rate of our reaction? And so this is just done graphically for us, and I didn't put it into the notes. Alrighty. But these are the values that are interesting to us. The rate at 0.4 molar is 2.963 times 10 to the negative fourth molarity per second. The rate at 0.8 molar is 5.926 times 10 to the negative fourth molarity per second. Now, they have negative signs because it is a negative slope, but I'm stressing that rates are always positive. It makes no sense to have a negative velocity. So I left the negative signs off. They're there by convention to remind us that reactants are disappearing. They're not telling us that it's a negative rate. What we're being asked then is, how does the concentration affect the rate of our reaction? So we generate these lists in a data table. List 1 represents time going by. List 2 represents the concentration. We graph that information, concentration versus time, and we solve just convenient points. Point 8 and point 4 were selected because they're half of one another. We solve to find the instantaneous rate by finding the tangent of the line, and that's a calculus move I'll show you in a bit. We did the same thing at point 4 concentration. We found the instantaneous slope. And all we're doing there is saying at that instant in time, we have a rate of molarity per second. We stand back and we say, how did the rate become affected by changing the concentration? And in my head, if I were trying to compare these two numbers, this is what it would look like to me. Times 10 to the negative fourth is the same for both, so I'll just disregard. 2.963 is pretty close to saying 3. 5.92 is pretty darn close to saying 6. If I doubled the concentration, the rate also doubled. 0.4 doubled is 0.8. 3 doubled is 6. When I double the concentration, the rate then doubled. Since the rate at twice the concentration is twice as fast as the rate, well, the rate law must be first order with respect to our reactant. It had nothing to do with the stoichiometry. The only way to determine this is to run the experiment. Now let me go back to the note pack. Again, I needed to pull those slides to show what we were comparing. So if you have your PowerPoint up in a different window, you can see those lists and how we go through and actually graph those. But the conclusion was this. Through the process of graphing, we said at 0.8 molar, the rate was determined through an instantaneous rate method to be 5.926 times 10 to the negative fourth. At 0.4 molar, we found the rate to be 2.963 times 10 to the negative fourth, and rates are given units of molarity per second. My logic was to disregard 10 to the negative 4. It's the same for both numbers. If I doubled the concentration, the rate did the same thing. Think of it this way. If I doubled the concentration, what power do I raise that number to double the rate? 2 raised to the first power is 2. This must be a first order reaction with respect to N2O5. Rate is equal to K times the concentration of that reactant, N2O5, raised to the first power. We say that it's first order with respect to N2O5. On a side note, the other reaction that we would study, we said we'd study zero order, first order, or second order. Suppose we doubled the concentration and the rate quadrupled. Doubling the concentration made the reaction go 4 times as fast. What order with respect to the reactant? Well, 2 squared gives us 4. If we see that pattern, it would be second order with respect to the reactant. And once in a while, we'll have a zero order, and that just means there's no effect. If I double the concentration, triple the concentration, there is no effect on the rate, and it just drops out of the reaction altogether. And typically that will happen for catalysts since they're not reactants or products. So a zero order no matter what we do to that concentration, I see the reaction rate not doing anything. It just stays the same rate overall as if I hadn't changed it. We call that a zero order. The only way to run this experiment, varying the concentrations, initial rate method, and recording the rate. Alrighty. So again, we say that this reaction is said to be first order with respect to N2O5. It was a direct power relationship. So in general terms, if we have, back to our general chemistry formula, A plus B going to C plus D, the rate law comes from the reactants only. In the initial rate method, there are no products. They're not considered. But in this equation, we would say rate is equal to K times the concentration of reactant A raised to some order, I don't know. I'm not going to put the little a here because it's nothing to do with the coefficient. Let me make up a different letter. I'll call it M. Times the concentration of reactant B raised to some other order. These little letters, M, N, P, Q, etc., we tend not to use the letter O because it can be confused with the number 0. Those represent the order with which those reactants are affecting the rate. Double the concentration, the rate doubles, it's first order. Double the concentration and the rate quadruples, 4 times as fast, we call that second order. So those exponents, M and N, are called reaction orders. The exponent is 1. The rate is a first order reaction with respect to that reactant. If the exponent is a 2, it's considered to be a second order reaction with respect to that reactant. We consider the overall reaction by adding the orders with respect. So again, reaction orders are those exponents in a rate law that indicate how the rate is affected by the concentration of each reactant. They must be experimentally determined, nothing to do with the stoichiometry. We said that a reaction is first order with respect to the reactant if the rate doubles and the concentration doubles. If we triple the concentration and the rate triples, it's first order. Whatever we do to the concentration, if the rate follows directly, it's a first order with respect to that reactant. We notice that a second order reaction, if I double the concentration of a reactant and the rate will quadruple, 2 squared giving us 4, tripling the concentration caused it to go 9 times as fast, 3 squared is 9, still gives us a second order overall, squaring the concentration to find the effective reaction rate. And we set a 0 order. No matter what I do to the concentration, it does not affect the rate of reaction. Therefore, it must not play a key role in the reaction mechanism. The experimentally determined rate law for the following reaction is rate is equal to K, NO squared times H2. Notice the coefficients, they may or may not match. There is a 2 in front of NO, but there's also a 2 in front of the hydrogen, but it's first order. So again, just stressing stoichiometry, nothing to do with the rate law. We would say, with respect to NO, it is second order. With respect to hydrogen, that's first order. And 2 plus 1 would be a third order overall. So reading this, we simply say it's second order with respect to NO, first order with respect to hydrogen, and third order overall for that rate law. Would doubling the concentration of NO have the same effect on the rate as doubling the concentration of hydrogen. If I doubled the concentration of NO and it's a second order, it's going to make the rate go 4 times as fast. But since hydrogen is a first order, if I doubled that, it only would double the rate. No, they would not have the same effect. Doubling nitrogen increases the speed more so than the hydrogen. Since the exponents are different, it would not have the same effect. Exponents are different. Most often when we're determining rate laws, we're given data. And we mentioned how we would change the concentration and run the experiment multiple times to see what's going on in terms of how the concentration affects the overall rate. Given the following equation, hydrogen peroxide plus iodide ion plus hydrogen ion forms products of I3, -1, and a couple of waters. This looks like a redox reaction. We're being asked to determine the rate law. Notice that no data is given for the hydrogen reactant. I have data for peroxide. I have data for iodide, but hydrogen doesn't appear. What we then assume is it's 0 order and it drops out. When we're asked to determine the rate law, think of the skeleton that we know so far. Rate is equal to K, that's our rate law constant, times the concentration of the first reactant, H2O2, raised to some power I don't know yet, times the concentration of iodide, raised to the order of which I don't know yet, times the concentration of hydrogen to the 0 order. That could simply drop out, or you may write it down with the power of 0. How does changing the concentrations affect the rate? If we think about trial 1, trial 2, trial 3, we're trying to find convenient trials that we could hold one reactant constant and see what happens to the rate as we change the other. In other words, if I look at trial 2 to trial 1, iodide is being held constant. It does not change. Therefore, it will not affect the rate. From trial 2 to trial 1, the only variance is the concentration of the H2O2. Therefore, it's the only reactant influencing the rate. Another thing I like to do as I'm considering rates is make sure I notice the power of 10. 2 of them are given to the value of -4. One of them is to a -3. So I've got to be careful if I'm thinking about these numbers. One convenient way might be 6.9 times 10 to the -4, 3.4 times 10 to the -4, and this is 0.14 times 10 to the -4. I could think of this in terms of the, equalizing the power of 10 as I try to decide how that reaction rate is varied. Another thing I do actually is get rid of the powers altogether. I could think of this as 0.69. This is 0.34, moving their decimal place over, and this would remain the same as 1.4. Whatever you need to do to just see it equally in your head. But please note that the decimal place is located in a different way. Alrighty. So think about trial 2 compared to trial 1, or you could think about cutting it in half with 1 to 2. When I think about the change in concentration of H2O2, trial 1 compared to trial 2, well, I notice that when I move up, trial 2 started at 0.05, trial 1 started at 0.1. 5 is exactly half as 10. I'm doubling the concentration. Moving from 5 to 10 is doubling the concentration. What happens to the rate in terms of doubling the concentration of H2O2? How do these two numbers compare? And knowing that it's lab data, it might be close and not spot on. But 34 doubled is 68. I'm noticing that's twice as fast. By thinking about doubling the concentration while holding the other guy constant and seeing that the rate also doubled, doubling 34 gives me 68. That's close enough. I believe this to be a first order with respect to the peroxide. Holding one reactant constant, taking a look at what happens when I manipulate the other. The next one we might want to consider, I want to consider trial 1 to trial 3. Trial 1 to 3 holds H2O2 constant, but doubles the concentration of iodide. I like holding one constant and changing the other. Therefore, the rate is only being influenced by the iodide. If I doubled the concentration from 0.1 to 0.2, consider this about 7 to 14. 7 doubled gives me 14. Doubling the rate of iodide, and again, you could hit this on your calculator, 1.4 times 10 to the negative 3 set over 6.9 times 10 to the negative 4 is pretty darn close to 2. You don't have to slide decimals. I'm just offering that as maybe perhaps an easier way to look at these numbers. If your mind can think small decimals, great. I like to think in terms of numbers I can visualize. So I would consider this as 7 and 14, or close to 0.7 and 1.4. But if I doubled the concentration, I clearly see the rate doubled as well. It's first order with respect to iodide, zero order with respect to hydrogen. We read this as rate is equal to K times the concentration of H2O2 raised to the first power. Iodide is to the first power, and hydrogen with no effect, power of 0. Let's talk more about this rate constant called K. K is a constant, and it actually has units associated with it. We can solve for K by just taking one of the trials and plugging in what we know. Once we have the rate law, I usually just select the first trial only because it's written first. The rate of 6.9 times 10 to the negative 4th molarity per minute is set equal to K, what I'm solving for, times the concentration of the peroxide times the concentration of the iodide. Both are raised to the first power, and the hydrogen, of course, just dropped out. I can solve for the value of K in the following way. From trial 1, but this is interesting. Since K is a constant, we indeed should get the same number no matter what trial I use. So rate from trial 1, 6.9, E negative 7, divided by 0.1, divided again by 0.1, and we get a value where K is 6.9 times 10 to the negative 5th. Let's think about units. What we have is a little formula to help us calculate this. The K units are found by taking 1 minus the overall order per unit time. 1 minus the overall order. Now remember, from this example, it was first order with respect to peroxide, first order with respect to iodide, zero order with respect to hydrogen. Overall, it adds to 2. 1 minus the total order of 2. 1 minus 2 is negative 1. So you can hit that if you don't believe me. 1 minus 2, negative 1. Alrighty. that concentration unit will be set to the order of -1. Now remember up here it was molarity, so it's molarity -1, and the time was minutes in this particular data table. It's going to be set over minutes, but generally you'll see that instead of writing it over 1, we'll just put it to the -1. So per molarity per minute is really molarity -1, minute -1. Let me repeat that. It's a way to solve for the K units. We used trial 1, plugged in the rate set equal to the concentrations raised to the orders with respect to each reactant, and solved for K. K is a constant. We could have used any of those 3 trials and it will come out the same number. To find the units of K, there's a formula. We start with 1, the integer 1, and subtract the overall order of the reaction. 1 minus 2 gave us -1. That concentration unit is molarity. Those little brackets stand for big M, molar units. So molarity -1, minute -1. That's the same as writing 1 over molarity times minute. But we'll see that written instead of as a fraction, but with the negative exponent. Pause here, take a look at the next example. Take a really close look at the data table and work to find a rate law. How does changing the concentration of A and B affect the rate? Are they first order? Are they second order? Work it out for a little bit and start the video again when ready. Let's see how you've done with this example. I notice that we have initial concentration of A, initial concentration of B, and an overall rate. I start looking through the data table to find, do I see a place where one of the reactants is held constant while the other changes? And that's the place I go to first. I'd like to hold one concentration constant so that it's not influencing the rate. Well, I notice in trial 2 to trial 3, the concentration of A is indeed held constant. Therefore, it will not be influencing the rate. And I notice that the concentration of B has indeed doubled. I can prove that by showing in trial 3, the concentration is 0.80. The concentration in trial 2 is 0.40. That indeed is doubled. Well, what happens to the rate? Again, comparing the rate in molarity per seconds of 14460 compared to 3600. That's probably mental math for some of you, but I'm going to check that out. 14460 set over 3600 gives me a value of 4. When I doubled the concentration, the reaction rate quadrupled. In terms of respect to that order, 2 squared is 4. This looks like a second order with respect to B. So here's what we know so far. Rate is equal to K times the concentration of A, yet to be determined, times the concentration of B, we just determined to be a second order overall. We don't know yet the concentration of A's influence. Interestingly enough, concentration B is never held constant. So we'll have to consider that when we look at how A is influencing. So we have a couple of ideas. We can compare trial 1 to 2, which would have doubled. And that might be easier than comparing trial 1 to 3, where we make it 4 times as much. You can pick either one. I think it might be a little easier if I consider trial 1 to 2, now knowing that the influence of the rate is second order with respect to B. So here's what we know. From trial 2, the rate is going at 3600. In trial 1, the rate is going 300. Let's find the factor at which it increased its speed. So 3 into 36. So 3600 divided by 300 shows us an influence of 12. The reaction is now going 12 times as fast. Alrighty. But we also know both reactants are influencing that speed. But we can factor out knowing that B is second order. Here's what I mean. When I look at trial 1 to trial 2, concentration of B is 0.4 to 0.2. It doubled. We know that this is a second order, so that just by doubling the concentration of B, the influence of this rate from that reactant is a second order power. It's 4. Let's factor out. It was going 12 times as fast, but a factor of 4 is coming from the influence of reactant B. Let's factor that out and find what's left. That tells us that 12 divided by 4, the influence of that reactant B factored out, leaves us a factor of 3 that must come from the reactant A. From the first trial to the second trial, the concentration of A was tripled. The rate is going 3 times as fast. Tripling the concentration and the rate follows directly makes it a first order with respect to A. I started with comparing trial 2 to 3 because I held one of the reactants constant. That allowed me to factor out and find a second order with respect to B. But because B was never held constant, I had to factor out its influence from trial 1 to trial 2. Notice how from 1 to 2 the rate is going 12 times fast. From that 12 times factor, 2 things are influencing it. We determined the influence of B, factored out that 4, that's 2 squared. Tripling the concentration of A left an influence of a first order overall. So we read this as rate is equal to K times the concentration of A to the first power. B is to the second order, its third power overall. To find K, we just pick a trial. I always pick trial 1, but for no other reason than it's written first. Its rate is 300 molarity per second. That's rate. It's set equal to K, what we're solving for, times the concentration of A raised to the first power, times the concentration of B squared to the second power. Let's solve for K and include the units. 300 divided by 0.1 to the first power divided by 0.2 squared gives us a K constant of 75,000. And let's consider the units for that number. Remember, our unit is molarity raised to the negative, well, it's 1 minus the overall order. Remember from up above, 1 minus the total order. Well, the total order here was 3. 1 minus 3 gives us a factor of -2. So molarity to the -2, and remember that time in this data table is seconds, so it would be per second, or second raised to the -1. The K constant has a value of 75,000. The unit on K, molarity -2, second -1. That's the same as writing 1 over molarity times second. We shorten that by putting molarity -2, second -1. It's seconds in this example because that's what the data table gave us. Up at the top here it was per minute. So I'm just kind of matching that time unit to what was provided in the table. Pause here and stare down the next data table. It sets up the problem here, but the data table is actually on the next page. Try it on your own first, then start up the video. Here we're looking at a data table for the reaction of BrO3 with bromide and 6 hydrogens to give us bromine and water. Again, that reaction provided on the previous page. This time all 3 reactants are given, and I have reaction rate data for each of these trials. So I have a trial 1, 2, 3, and 4 that we can use to compare, knowing that we're looking to find the rate with respect to each of the reactants. So rate is equal to K times the concentration of BrO3 raised to some order yet to be determined, times the concentration of Br raised to the order yet to be determined, and H plus, same story. Here we have 4 sets of data, and I'm going to stare down and try to find best I can where 2 of the reactants are held constant and only 1 is changing. And I can see that pretty quickly between trial 1 to trial 2. 2 of the reactants do not change. The first reactant is doubled. So the only thing influencing the change in rate is our first reactant. Again, notice that I have a -4 power and these are -3 powers. I want to just make sure that I'm looking at them in the same way. So I'm going to make this guy be 0.8. 0.8 times 10 to the -3. And that way I only have to consider the following numbers. 0.8 compared to 1.6 compared to 3.2 compared to 3.2. It's just an easier way to handle that data in my mind, at least. When I notice that BrO3 is doubled from trial 1 to trial 2, 8 doubled gives me 16. 8 times 2 is 16. The rate doubled as well. I bet you determined that it's first order with respect to bromate, BrO3 negative. Trial 1 to trial 2 was useful in finding the first reactant. I notice between trial 2 and 3, I'm holding 2 reactants constant and only changing bromide. I'm doubling bromide, the other 2 are left constant. Therefore, the only thing influencing the reaction rate is the middle guy, bromide. If I'm doubling the concentration, what happens to the rate? Doubling the concentration over here doubled the rate as well. In my head, I go 16 doubled is 32. 16 times 2 is indeed 32. So these are indeed factors of 2. So doubling the concentration doubled the rate. It's first order with respect to bromide. One more to determine. Can we find a place where they're held constant? Oh, I see it. Trial 1 to trial 4. Trial 1 and trial 4 hold the first 2 constant, so they are not influencing the rate, but I'm doubling the hydrogen. So the last guy is the only one influencing the reaction rate. What happens to the rate from trial 1 to trial 4? 3.2 over 8, I guess I'd go 8 into 32, comes out to be 4. So doubling the concentration made the rate go 4 times as fast. That's a second order with respect to hydrogen. First order with respect to bromate, first order with respect to bromide, second order overall. We were also asked to solve for K, the rate constant. And for no other reason than it's written first, I tend to use the first trial. The rate of 8.0 times 10 to the -4th molarity per second is equal to K, that's what our target is, times the concentration of bromate from trial 1 to the first power, times the concentration of bromide to the first power, times hydrogen to the second power. Solve for K. We would hit 8.0 e -4 divided by 0.1 to the first power, divided by 0.1 to the first power, divided by 0.1 squared and we come up with a number 8. This has a rate constant of 8. And let's consider units. The concentration unit here is molarity. Remember the formula, 1 minus the overall order tells us with what respect to Ray's molarity. Well, we have first order from bromate, first order from bromide, second order from hydrogen. That's a total of 4. 1 minus 4 gives us a value of -3. Molarity to the -3rd, time here is in a second, and it's set under also, so we go second, -1. So that would be writing 1 over molarity times molarity times molarity times second. Instead of writing it this way, we'll see it written in terms of molarity to the -3rd, second to the -1.